So today a video about this thing. This is a 5-port gigabit switch. This is not your normal 5-port gigabit switch though. This one has been engineered to have one port on the back of it. It also has this connection to a Pine64 A64 LTS here. The purpose of this is to actually manage the switch, because this is a switch chip that's used in both managed and unmanaged switches, and it has an interface on it to actually control the settings inside the switch chip. This bus is called SMI, and it is almost SPI. The chip actually does have a driver in Linux already, which makes this pretty easy to get up and running. And the only requirements here are a board that is loading device trees, so it has to be like an ARM board or RISC-V, but it won't work on an x86 board because those run on ACPI, not on device trees. While the drivers are in Linux, it is pretty hard to actually find hardware to use the drivers, and that's why I customly designed this switch board. It's pretty simple PCB. It has a Realtek RTL A367S switching chip on it. Has a few solder bridges here. Let me get that closer. It has these soldering bridges on it to control a few GPIOs that will be changing the settings of the switch chip while it's booting. And this is all because these settings are not documented very well, so I had to make this configurable on the board, and the second revision will not have this. It also has a header here to control the switch chip. This is a regular pin header, except I've labeled it here as SDA and SCL because on the same GPIOs it's doing both I2C and SMI, but I2C is for talking to an EEPROM chip that's not on this board. There's also a footprint here for a USB-C connector to just power the board while this is not in use, because if you do not connect anything to configure the chip, this will just act like a really weird 5-port gigabit switch that's just a dumb switch. So on this board I have actually connected a pin header. I've actually soldered a pin header on it, and it's connected to the Raspberry Pi header on this board. It does not matter which GPIOs it's connected to, as long as it's connected to a GPIO. And this works fine. It should work on a Raspberry Pi. It should work on any board that has GPIOs available on a pin header. You might be wondering what the point is of having one backwards facing Ethernet port. The use case is this. This is a 19-inch rack case. It's missing the top, and these are pretty cheap project boxes if you want to make anything that fits in a standard server case or portable case. And with this switch chip, it can have 4 forward-facing Ethernet ports connected to the front panel here, which will be laser cut, and it can fit here beside the post here. Then an internal network cable can go here to a single board computer. It won't be this single board computer though, but it works as a mock-up. This will be going together with this sound card, which is designed to also fit in this case and has a hole in it to fit over a mounting post to fit more clearly in this case. But that is something for a later video. So let's have a look at this switch as it's implemented here. I will boot it up because this does not act like your regular network connection. Of course you will have your normal network connection of the SBC, and this will be just the Ethernet 0 device. But with this driver loaded, these ports will be showing up as separate network interfaces in Linux. And in my case, I've defined them as LAN 1, LAN 2, LAN 3, and LAN 4. And the driver in Linux provides a lot of the abstraction to make sure that this works as it we are actually separate network interfaces. But if you actually create a bridge on Linux and bridge two ports together, those will be handled by the switch chip instead. So you don't actually need to send the traffic to the single board computer. That does not actually concern the single board computer. This is actually similar to the internals of a lot of cheap Ethernet routers. It will have a processor in it and it will have a switch chip in it to control external facing ports. So let's switch over to a screen capture.
So this is an HDMI capture of the A64. And if we load the kernel log here, you will see that it has detected the switch chip. The Realtek SMI driver here for, SMI connected Realtek devices has detected that it is the correct model of switch. I have not connected an interrupt pin here, so it complains about that, but it works fine because it can still pull it. And it has not set up the connections. And in the IP command here, I can see that I have the LAN 1 to 4 network interfaces in addition to my F0 device. And everything is down at the moment. If I now use the IP tool to bring up my normal interface, it has not done anything. There you go. I was a bit too quick. So now the normal interface is up. It is possible to bring up the virtual interfaces for the switch chip. And that is done exactly the same way with the IP utility. It's important to remember that while it shows LAN 1 at F0 here, the actual interface name is just LAN 1. It's just a display thing. So I will bring them all up here. And now if I run the list command, instead of down, they are now marked as lower layer down. That is because I have not plugged in any cables into the user-facing side of the switch yet. At this point, the Realtek driver did configure the switch port though for managed routing, where it will forward packets to the F0 interface here. You can see here that it has configured my 4 switch ports. Let's rerun that with the W option to have live updates. If I now grab my network cable and plug it into port 3, there you go. It will detect that a cable is plugged in and that it has a full duplex gigabit connection here. Yep. Yeah, the power connector on this board is a bit broken and I bumped it too hard, so it is rebooting. So I've run the same steps again now after the accidental reboot and I'm in the same state. It just doesn't list here that it's plugged in at the bottom because the cable was already plugged in. And if I run the link now, the state of interface is up for LAN 3. One of the neat things now is that I can create a bridge interface into Linux with the bridge.ctl command. Let's call this one LAN. Right, it's brctl because Linux cannot type too many letters. And now I have a LAN interface. And now I can just add all the 4 user-facing ports of the switch to the bridge. And yeah, it does not show any details here. I can just go bring the interface up. A LAN. And now the interface is up. At this point, the driver has configured the switch as actually switching between the ports. There's a lot of logging. Most of it is from the actual bridge driver in Linux, not from the Realtek SMI driver here. Now I can just do regular Linux networking things and give this interface an IP address. If I can type correctly. on the bridge. And then let's ping Google. Does it work? It works. Networking through the switch chip with a Linux bridge pretending to be a real switch. Or actually a real switch pretending to be a Linux bridge. And we'll see, IPv6. Of course, I have not added a route yet, but it works over IPv6 at the moment. Yeah, that's basically how this works. You get new network interfaces in Linux by magic. All the normal utilities should just work with it, like ftool to get statistics. It is a capital S. Gets all the regular SNMP statistics of a network port because it's a standard and the switch chip provides the same SNMP values as normal Linux kernel does for interfaces. And if I don't give an option, you get all the normal link information that also just works. And I should install Beamon here because I believe all the interfaces are emulated enough that graphical tools, well, graphical in quote marks, should just work on these interfaces. If I go to LAN 3, you can see regular broadcast traffic on my network going on here. So that's basically a quick overview how switchdev and DSA, the distributed switch architecture in Linux works. This will probably work better if you have more fancy switches that are actually designed to do this, but it works for this case. And well, the target for this switch, the PCB, is not to be ended up with an ARM board. It will be connected to an x86 device, so this does not even work with this hardware. But it will be connected up to a microcontroller, so Linux can at least see port status. And that is especially important if you have DHCP on the network and you want to make sure that if the cable is plugged out and plugged in, that it does DHCP again to be up to spec, because you might have switched a network. And yeah, that's actually all of it. Thanks for watching.